we focused yesterday on two new terms, mass defect and binding energy, that went with both fission and fusion. Remember, fission is those reactions whereby we take one heavy nucleus and split it apart into two lighter nuclei. We got to prompt that to happen. We got to kickstart it to happen by firing a high energy neutron at it. Okay, it gets absorbed, breaks apart into two lighter nuclei. We get some more neutrons. Those extra neutrons that are produced cause more reactions to take place. We get a chain reaction. In a nuclear fusion reaction, we get two lighter nuclei that are prompted to fuse together by energy, form one heavier nucleus, produce more energy than we put into it. That more energy, some of that can go into fusing more nuclei together and cause a chain reaction there. In both cases, we get a lot of energy released. A fission reaction, depending upon the exact fission reaction that takes place, may be in the range of 200 mega electron volts. A particular fusion reaction, we get a little bit less, but pound for pound, kilogram for kilogram, we should say, we get more out of a fusion reaction. So per kilogram of fuel, or per 50 kilograms of fuel, or per 100 kilograms of fuel, we get more out of fusion than we get out of fission. Nuclear fission, you remember, the products of nuclear fission are radioactive. The products of nuclear fusion are relatively harmless, not radioactive. Now, why do we get the energy out of both fission and fusion reactions? Well, it's because of this mass defect thing. We define mass defect in a couple of different ways. One, in the context of the nucleus itself, and then one in the context of the fission or fusion reaction, which really just comes from the definition for the single nucleus. How do we define mass defect for a single nucleus? Well, it's the difference in mass between the nucleus and the nucleons. You guys remember what the nucleon is? Give me an example. Give me an example of a nucleon. Okay, we all know what the nucleus is, right? Give me an example of a nucleon. Adam, what's an example of a nucleon? Good. Protons and neutrons make up the nucleus. When we add up the mass of the protons and the neutrons, we don't get the mass of the nucleus. In fact, the nucleus itself ends up weighing just a little bit less than the mass of all the protons and neutrons combined. And that's really odd, but it is what it is. Okay, the binding energy is the energy that's required to disassemble the nucleus, so to rip it apart, to take apart that nucleus. It would correspond to the energy equivalent of the mass defect, right? We've learned this equation back in our last unit, the energy mass equivalence equation. If we rearrange that to solve for mass, then the mass equivalent, if we keep it in the same form that it's in, the energy equivalence of the mass defect would correspond to the binding energy. Remember, that's the speed of light squared. Now, how does that manifest itself in a fission or fusion reaction? Well, when we have a reaction, we lose a little bit of mass. The reactants, or we should really call it the parent nuclei, started with a certain amount of mass, but the daughter nuclei weigh less, just a little bit less, but still less. We call that mass defect. The energy that's released in the reaction comes from having a little bit of binding energy left over when you rip apart nuclei. Okay, when you take apart those nuclei, rearrange the protons and neutrons, sometimes, as in the case of a fission or fusion reaction, we have a little bit of binding energy left over. And that binding energy that's left over gets released. That's our 200 mega electron volts of energy. Or that's our, as we saw in the example that we did in class yesterday, what was it, 174 mega electron volts of energy. That's our, whatever we get in our homework questions, okay, the energy that's released from the reaction. So our homework was page 819, 1, 2, and 3. Let's do question number 2 and 3, because they kind of go together, right? I think if you can get into question number 3, I think you're probably going to be okay with question number 1. If not, let me know, and we'll take a look at it. And remember that tomorrow, when we have our quiz tomorrow, that's going to be a fission-fusion quiz, okay? All right, so we got number 2, says uranium-235 nucleus absorbs a neutron and then splits into bromine and lanthanum. Uranium-235 has an atomic number of 92. I remembered that because that's a pretty common one that we use, but I'm not trying to memorize that, right? It just happens because I've used it 1,000 times. If we don't remember that it's atomic number 92, where do we get that information from? Periodic table, right? So that uranium-235 absorbs a neutron. It doesn't really matter which side the neutron goes on. Has to go on the left side of the equation, but which comes first, the uranium or the neutron, doesn't really matter there. It produces bromine 87 plus lanthanum 146 plus neutron. How many neutrons do we get here? Let's leave that off right now, actually. Okay, we know we're going to get neutrons produced here, but let's leave it off when we're trying to figure out how many neutrons. Okay, 92 plus 0 is 92. 35 plus 57 is 92. So we're okay with the atomic number balancing, right? We're okay with the charge, right? Conservation of charge, as we saw in yesterday's quiz. What about the mass number, or the conservation of nucleons, as we saw in yesterday's quiz? 235 and 1 is 236. 87 and 146 is 243, I think. 243. How many neutrons do we need to balance this? If we got 236, sorry, this should be 233. 236 over here, 233 over here. How many neutrons do we need? 3. That's the same as in the example that we gave you, right? Same as in the example problem that we gave you yesterday. 3 neutrons were needed. That's not always going to be the case. Sometimes it might be 2 or 4. So look at each question individually. Plus, we get some energy release there. That's really what we're trying to find in question number 3. What's the energy release? Okay, so how do we go about doing this? Well, remember, energy comes from mass defect, from the missing mass. So let's get the mass defect. Let's get the missing mass. But to do that, we got to get the mass on both sides and then subtract them. So let's do that. What was the mass? What was the mass? Anybody here of uranium-235? 235 point. Yep. 043. 930. Thank you. And what was the mass of neutron? 1.00 something. 8665. Thank you. Remember, those are all in atomic mass units. What about bromine? I'm going to say 86 point. Don't everybody speak at once. Yeah. 920. Okay, and lanthanum 146. 145 point. Yep. Okay, plus 3 neutrons, and of course we know what that is. 3 times 1.008665 atomic mass units. All right, what do we get when we add up 235 plus 1? 236 point. See that lightning quick math there? 236 point something. I'll leave you guys with the rest of it. I've done the hard part here. 235 plus 1 is 236. Let's see. 0, 5, 1, 2, something. Yeah, that's what I was going to say. 236.052595. Good. On the right-hand side, we start adding up the black ones here. 86.9 plus 145.9 plus 3 point whatever. What do we get on the right-hand side? 235 point something, probably. I'll give you the first 2 digits. You guys. 249. Thank you. We knew it was going to be less than 236.05, right? Because we have to lose mass. Otherwise, we're not going to get any energy released here. All right, let's get the mass defect now. The mass defect is simply subtracting the 2. 236 minus 235, 0. I don't know, 3-ish? 2? 0.2? Al, you got that? 180. Thank you. Now, what are we going to do with that? what are we going to do with that? Tyler, what do you want to do with the mass defect now in atomic mass units? There's your hint. What are we going to do with the mass defect in atomic mass units? Aiden's letting you off the hook there because he's raising his hand. Oh, okay, go ahead. Yeah, let's convert it to kilograms. Good. And we're going to do that by saying one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. That conversion's on our data sheet, right? Equals 0.180098 atomic mass units over X kilograms. So let's get the mass defect in kilograms now. Who's got that value? 2.98963 to the minus 28 kilograms. So in one particular reaction, where one nucleus decays, we lose 10 to the minus 28 kilograms, which is a ridiculously small amount of mass, right? But when it starts growing exponentially because of a chain reaction, still small mass, but the energy starts becoming pretty big. All right, now we just gotta find the energy here. So we're going to multiply the mass defect by c squared. And what do we get there? .69 times 10 to the times 10 to the minus 11, and that's going to be joules, right? All right. Now we want to convert that to. Doesn't really say we have to convert it to electron volts, but that's what they have as our answer. So let's do that. We know that 1 electron volt is 1.6 times 10 to the minus 19 joules. So we're going to say X electron volts is 2.69066 times 10 to the minus 11 joules. And I'm going to say that X is going to equal 1.678 times 10 to the, what is that? 10 to the, is that right? Which is 167.8 mega electron volts. Okay. All right, let's have a look at 3 questions, 3 multiple choice questions yourselves. First one, 166. I'll give you about 45 seconds to answer 166. All right, let's have a look. I got some information here. They're giving us some background here that might be interesting. In fact, it's important, the discovery of nuclear fission, but it's not really relevant to this question, right? All we're doing here is balancing an equation. Kind of interesting, though, isn't it, that the discovery of nuclear fission was made by Germans, by Germany, as opposed to by Americans. Okay. In fact, that's part of the reason why the Americans got into the nuclear race, right? It was because they were afraid that the Germans would get the bomb first and obliterate them. Then it never actually got used against the Germans, of course. But I got many possible fission reactions, that can occur, 2 of which are shown below. We want to know how many neutrons are produced right here in the second reaction. So effectively, again, we're just balancing it out. 1 plus 235 is 236. We can see that, right? Because they've got the intermediate step listed there. They don't really need to list that intermediate step, but they do. 236 on the left-hand side, 92 on the left-hand side. 140 plus 92 gives me 232. 54 plus 38 gives me 92. All right, how many neutrons do I need? How many neutrons do I need to make this into 236? Yep, good, 4. We need 4, 0, which we can't really have something that's 4 zeros. So what we have is 4 of 1 0 neutrons. Good. That's the first time we've seen one that's been something other than 3, right? Okay, but I told you, be prepared for that. Sometimes it's 4, sometimes it's 2. Usually it's 3, but not always. All right. got two more equations that I want you to work, or two more questions, sorry, that I want you to work on. Question 167 and 168. I'll remind you that before you tackle these questions, that in your homework questions, you found the mass defect in the energy release, the binding energy, in an equation in fission reactions. But remember the other definition for mass defect and binding energy, okay, in the context of the single nucleus. Okay, that's what you got to look at here for this one. Okay, see what you can do. All right, let's have a look here whether we're finished or not. It says the information says the measurements given below indicate that uranium-235 nucleus has a smaller mass than the mass of the corresponding number of free protons and neutrons. The difference in mass is called the mass defect. Hey, they're doing us a favor here, right? They're defining mass defect for us. If we forget what the definition is, they're giving it to us here. They're also defining binding energy here effectively. It says the energy mass equivalence or mass energy equivalence equation can be used to predict the energy that binds the nucleus together by using the mass defect. Here's the mass of uranium-235. Here's a proton. Here's a neutron. We want to find the mass defect. I want to know how many people did this. I want to know how many people said 1.6726 times 10 to the minus 27 kilograms plus 1.6749 times 10 to the minus 27 kilograms. Added those up and got the total mass of the protons and neutrons. Nobody wants to volunteer that they did that, but I'm sure lots of people did. Okay, I'm sure lots of people did. What's the problem with that? Joseph, what's the problem with that? Yeah, we don't have a single proton and a single neutron in a uranium-235 nucleus, right? How many protons we got in uranium-235? How many? Just say it. 92. If we have 92 protons, then we got to multiply this number by 92. And if we have 143 neutrons, we got to multiply this one by 143. When we do that, what do we end up getting for the mass there? 3.933.899 times 10 to the minus 25. All right, look, we got a number that was slightly bigger than the mass of uranium-235. That's what we should expect. Remember, mass defect is the difference in mass between the nucleus and the nucleons, but the nucleus is slightly lighter than the nucleons as it is here. So don't write this down as your answer. Okay, we don't want to do that either. We want to subtract the two to get the mass defect. So we're going to say 3.933899 times 10 to the minus 25, subtract 3.9021 times 10 to the minus 25. And what does that equal? That's really what we're looking for here, right? Joseph, you got that? 3.799 times 10 to the minus 27. Okay, we're looking for just the base here to 3 digits, because they tell me 3 digits here, right? So we'd express that as 3.80, right? Yep. 3.1799. Okay. Joseph was just kidding. 3.1799. So we're going to say it's 3.18. We'll express that as 3.18. Or for all you French immersion kids out there, 3.8818. Good. All right. Now the second question is easy, right? If you get the first one, the second one's easy. What's the binding energy? All we're going to do in this is say E is equal to mc squared. M is 3.1799 times 10 to the negative 27 times 3 times 10 to the 8. Boy, that's a little messy here, all over the place. Squared, what do we end up getting for that? Get that, Zach? Get that, Zach. 2.862 times 10 to the negative 10, okay. And that's going to be measured in joules, right? They tell me they want it in the electron volts, so Let's do that conversion. Not quite as easy as I thought, actually, because we have to convert it to electron volts. 1 eV over 1.6 times 10 to the minus 19 joules. That conversion factor is on your data sheet. Equals X eV over 2.862 times 10 to the minus 10. What does that equal? Kate, when you got that one? Value of X? Oh, okay. Okay. Lisa? Okay. Anybody else? Yeah, okay. That's okay. That's okay. Instead of something. Okay. It doesn't really matter what the exponent is there, right? Because we're just looking for the base anyways. We'd express that as 1.79. Good. All right.